So welcome. We are hosting today Sang-ho Yoon, and welcome here. And so Sang-ho is an assistant professor of Graduate School of Culture Technology at KAIST. And right now he's leading the Human-Centered Interactive Technologies Lab. And actually, before joining KAIST, he was at Microsoft and in the Applied Science Group. And actually, we collaborated together in the past, so that's kind of how we met. And he has a PhD from Purdue University. And his research focus is natural interaction, novel sensing techniques, and also haptic experiences and next generation of XR interface. And that's what he's going to talk about. So welcome and thank you so much.
Yeah, thank you for the introduction. And I'm really glad for you to hear my presentation. So I think I can go for maybe 40 minutes presentation. Yeah. So just briefly, I'm going to talk about the beyond glasses. I actually put the bold title because actually I'm going to talking about the workshop about this beyond glasses stuff. So that's why I put it there. So it's about the future directions for XR interaction with advanced sensing technique and haptic design frameworks. And actually what I'm mainly working with is these two parts, the sensing technique and the haptic design frameworks. That's why I come up with these titles. So just briefly talking about my background, I actually work at ASG from 17 to 20, and I was working on the sensing and haptic interface or devices at the time with the interaction scenarios here, and I moved to Samsung Research with the AR lab, and actually came back to academia in 2021. Yeah, so I'm mainly working on the interactive sensing techniques, haptic interface, and the authoring toolkits. Yeah. And currently, I have 9 PhD and 11 master students, and that's why I'm here. So whether my students can be later, if they are really interested in industries, that's why I'm here, actually. Yeah. So this is our lab overview. This is actually what I actually demoed. We did a whole lab demo in this year's CHI, and this is what we demoed at the conference venue. We actually demoed like more than 6 demos with these devices and the interactions. And it's from the embedded interactive technology to advanced interaction methodology and the user interface. I'll just skip this one. And today, I think I just have 2 pages about this, but why I'm talking about beyond glasses is that I think when I was working at Microsoft and Samsung, the problem was that the hardware has an issue, like display quality, computing power, battery life requirements, and it's actually getting resolved, in my opinion, because even in the Samsung or companies, they already formed the product team in the actual business group. So that means they are actually geared towards moving to this business side. And so still interactions is based on the hand tracking and gaze tracking. And it's actually in research academia point of view, it's already commercially fulfilled in terms of we don't get the very precise hand tracking, but I don't think there will be a marginal increase in improvement for the tracking in near years. So I think that's what we are seeing, that the gaze and the hand is there. Yeah. But currently, I think this is what people have done in the MSR before, or Meta doing, is that, but still the future direction in XR interaction is really need to leverage the human body, interacting object, and surrounding space. And it requires the understanding of context and deeper intentions from the user. And I think the enhanced sensing technique to understand user's motion, interact with the contact with the object and user behavior in the space is what I hope to work. And I'm actually currently tackling the first 2, the user's motion and interaction with contact with the object. So I saw recently what's happening because WIST was there last week. I think it was last week, yeah. And they had they had the context with the interaction contact with the object. This is from the PTC where they already work with the user's behavior in the space. They already record the whole motion of the workers, and they can actually get the analysis out of it automatically. And even with the LLM, they can actually pinpoint where the workforce is stay longer. And this is actually from the Sigma. Yeah, I put excerpted from the Sigma paper, and it's we are doing already collection on those multimodal data set. But another thing we are missing currently is, I think, the physicality in the XR scene, and needs to bring the essential multimodal physical feedback, meaning that currently we are keep ourselves depends on the buzzing. the vibration only. But there can be force feedback, thermal feedback, which hasn't been really explored, and that's actually one of the research area that I'm also convinced to work into. And the other one is the entire haptic feedback with ease. So what this means is that currently all the haptic design is done by the either researchers in the field or the students, because it requires the coding. And I think to move forward, this haptic feedback really need to be designed without the coding and with the ease for any designers. Yeah. So I think I'm talking about more about the other-body interaction. So that's why I was talking about advanced sensing techniques. I think these three things I am mainly focusing on. So first one is the microgestures, based on the context aware of the microgesture and the richness of the microgesture. I'll talk in a minute. And hand tracking, rather than hand tracking, is already it's not my main interest. It's the interest from the vision community. So my interest is what can go beyond the tracking of the hand. So currently, our lab's focus is the hand force estimation. So you can get extra information from during the grasping or during the occlusion what's happening. And in terms of the gaze tracking, there are already gaze tracking with a good frame rate and the accuracy. So our main focus is more about what interaction intentions we can get out of the gaze. So maybe grasp intention, whether they want to use the device, the object, or they want to move the object in the VR scene or MR scene. And on the haptic design framework side, I think initially when I came back to academia and worked for first 2 years, I heavily worked on the multimodal input-based haptic rendering because there are already lots of the audio and visual data we can convert to the haptics. That's what I have worked on. The second one is the multimodal haptic interface. Actually, I built the device, the wearable device, to actually give the actual feedback, force feedback, or thermal feedback, which I actually present in ISMAR at Bellevue right now. And third one is the embedding haptic experience with AI. So I'm actually currently working on, I have started working on from the year and a half now, and I'll talk about detail, but it's more about how we can leveraging the contextual information to the actual vibration or physical interactions. Yeah. So this is a scheme of our lab's work that we present in the Kai interactivity. And it just shows a glimpse of our works in visualization, but I will just go one by one detail. So currently, I will first touch with the advanced sensing technique side. So today, I think I will mainly talk about this lab 2, which has been done. So the context-aware hand interactions based on the bioacoustic sensing and the posture infomuscular force estimation with the hand skeleton information with the EMG. And on the right side is the works that is in progress, is work in progress, meaning this one is actually submitted for venues now under review, and it's for the microgestures with the rich interaction with the continuous input, and there's a gaze-assisted hand interactions for VR. So I'll just go briefly for this bioacoustic sensing. And for this one, we actually tackle this problem because we are interested about how we can have the different tap and swipe for the different contexts. So here you can see from the figure that this user has a different context. So whether he holds the box, or he's actually tapping on the surface, or he's just tapping within his hand. So we want to figure out whether this can be figured out using the bioacoustic sensing, active and the passive. So the main idea here is to get the small movement of object or the digit that do not require the moving the whole hand. So this is just the video that I think can give you the overview. So we use the active signal from the speaker and the passive on the finger from the IMU, so we can get the different context of the tap and swipe gesture done. So basic idea is we have, yes, a little bit there, but we have the passive acoustic, which is the bone conduction sound propagation when you are moving your hand just by yourself. And we have an active acoustic, which can actually give out the actual signal out from the sensors. And by using those two different kind of modality, we can get the better signals out of it. So we are actually using the wide spectrum. So for the passive, we use the frequency range, the vibration, whereas using the active one, we use the high frequency range. So we get all different sort of the wide spectrum bioacoustic sensing done with this device and setup. And this is just the prototype of what we have done. So we actually put it on as a wrist and the finger side, and we actually focus on putting just the small actuator on the finger, so we don't need to really equip with a big one. So this is are the requirements for the actuators for this configuration. And this is what we are trying to do with the interaction context taxonomy. So what we are trying to do here is we are trying to dissect into these three main areas within hand, surface, and hand grasp. So that's the typical usage of the hand taxonomy in the microgestures. And so then we move on to the specific types of the object or that we are dealing with. So whether it's the rigid object, soft object, or whether we are dealing with a different shape of the grasp. And we collect the data and we train and test the data with the tap and swipe on this one. So you focus on the sum and the index because that's the maybe more than 90% of area when using the microgestures. Yeah. So in terms of the system workflow, we had to have this context binding to avoid any force trigger. So after simple just tap, then it actually go to the context binding stage, and we can actually do the tap or swipe with a different context wise. Yeah. So this one actually prohibits lots of the force trigger when we actually do the test in the field. So this is a whole work frame, but it's just briefly, we just utilize a multiple SVM classifier. So this one doesn't require that much training or the computational cost because we are getting lots of the rich data out of it. So based on this result, we compare with whether we use active omni or passive omni or active and passive both. So previously, there are many papers dealing with the active omni cause or the passive omni bioacoustic, but it's rare to see that this active and passive together. So we see that there's an increase in this accuracy there. And second part is using this posture-informed muscular force learning for robust estimation. So here the concept is with the data glove, we get this full data training. So we have this data. It's based on the glove. The sensing is based on the glove. So we have this mocap. It's not, the actual vision-based mocap, but it's the accelerometer-based mocap device that we get the skeletal 3D hand pose, and we get the EMG. And we also have this glove is pressure sensitive on the whole palm. So you can get the whole 64 levels of the pressure on your hand. So you can get the rich data out of it. So based on that data, we trained on it. And when we actually run it with the raw camera with the EMG, we can actually get the good grasp estimation or the hand force estimation in each area of the hand. Yeah. So we actually data collection from 20 participants and total of 83.2 million of frames have been collected. So we maybe use too much for the users, but each user maybe contribute to more than 2 hours in our study. Yeah, so we actually came from the different types of grasp, but we didn't use just normal grasp. We actually extracted 10 grasp gestures from the standard 33 grasp types, and it's covering all types of grasp types. So these are the 10 main grasp we are actually working on to get the data. And this is compared to the state-of-art data set. So we have the similar, maybe less participants, but our frame is much more than that. And we covered our pressure, pose, whole hand, and natural object all together. Yeah, so based on this, we have this accuracy here is that we actually do the ovulation study. So we see that even only with the EMG can give you some level of the pressure estimation, but with the posture estimation. So here the difference is that when you just use the egocentric camera or the raw camera, usually they use the hand angles only. But in our case, we use the skeleton data itself. So we use I think, more than 16 sets of the coordinates of the skeleton data, and we actually get the much better accuracy in terms of whether we have the tooth. One of accuracy here refers to whether each part has been touched or not. That's one of them. And this R-square value is actually its regression value. So we have much higher than the previous state of art, which has been published previously in the SIGGRAPH or other venue. They have around like low 80s or high 70s. So we have much higher accuracy. And this is the whole architecture here. And this is what we have to focus is in the train session, as I mentioned, we have the different setup because we actually want to have the occlusion-free ground truth data. So we, based on the glove to get the skeleton data. And in the real test session, we actually, when they capture the hand, we use the state-of-art hand reconstructed skeleton model. So it can actually get the good, even there's occlusion, we can get the some levels of the skeleton. We can utilize it to get the, do the testing of the inference, the hand pressure out of it. And this is the qualitative results. And we can see that the right side here is actually our work. And it can classify different, this intensity of the color is actually showing the different intensity of the pressure. So we can get the accurate pressure even with the occluded with the object. We did it with all different types of the grasp types, so it actually worked out. And this is just showing the video of what working. So we can prove to the reviewer that it's actually working in real time. So on the right side is our work. And we show that the 3D hand pose is actually gained from the camera view. And this is, we use the conventional model here to extract the skeleton. But our main idea is to get the pressure level out of it. Yeah, and that will be actually been present in the NeurIPS this year. And based on that, other than that, we have two work in progress for the sensing technique. One is on the utilizing gaze tracking. So here, what we are trying to do is the pre-grasp helper. So what we are trying to do is we can actually automatic preparatory virtual object manipulation using just the gaze. So the thing about the gaze is it's really good at getting the cursor moving or selecting. But we want to see whether, even when you look at the same object, there could be two different, there can be different intention. So here we see that in the VR object, main intention is in two folds. One is actually they want to move it, manipulate it, or the other one is they want to use it, like the pot. Like for the pot, they want to get the water out there, or they want to use it for drill. In VR object, they have different purposes. So we want to see whether if we know it's they want to just manipulate, we can actually provide a preparatory this manipulation. So the main idea here is that the people had hard time actually getting into the VR object when they're in the VR. Even if it's far away, they don't really want to walk there and grasp it. So for the manipulation purpose, we think that is the right, we want to see whether we can actually discriminate those two different intentions. So it's our very initial work. And what we are currently doing is that we see that we are collecting data. I think we are almost done collecting data now, but I think when we collect the data, we see some different data patterns from the gaze. So we are using the Barrio headset right now to get the gaze. And I think that gaze is based on the 200 frame rate, but what we are trying to do is see is that whether we can discriminate it. And we observe some the preliminary result that it can actually discriminate it based on the data analysis we have done. So we use I think there's a recent papers with the gaze. They are, I think, more than 10 different features they use for the gaze detection. We also utilize it, and we actually added more for our own purpose. And second one, the working process we are doing for microgesture is actually rich and continuous microgestures. So even for recent works in microgesture, it's more about the tapping or self-touching on your body. So here, what we want to do is whether we can actually utilize the thumb and the index to make the continuous mouse working on the hand. So here, we actually look into two different types. One is whether indirect pointing is workable with the microgesture. And for the thumb click, what we have to consider for our thumb click behavior. So we actually found out, we actually came up with our own configuration. So we have set the configuration with this joints relationship between the thumb and the index here. And we can see that the relationship between thumb and index can be used for the continuous tracking with the relative position starting point. So this is our basic idea. And for this one, this is how it's working in real time. But she's using the keyboard for getting the data collection right now, but it's actually working in real time with the just thumb and index with the egocentric camera. So that's what they have done right now. And from this study, we are not just working about getting the this thing working. That's not our main purpose. Our main purpose is to get the behavior of the sum and the index during the continuous moving and during the sum click. Whether we can actually get how much threshold or boundary we have to have for the sum click to work. Those things are actually measured. We use the OptiTrack to actually collect the data, and that will be actually the part of the analysis as well. And now moving on to the other half is that we are working on this haptic design framework. And let me just go through this one. Yeah, I think I have to. Yeah. So I initially working on the multimodal haptic rendering based on the multimodal input. Here multimodal meaning the visual input and the audio input mainly. And the next one I work on is a multimodal haptic interface. So actually, this one is actually happening simultaneously. In our lab, we make device. And half of them actually make their own device because there's no commercial one, or we need to modify the commercial one. And half of them is working on the rendering part, which is purely the algorithm part. And last thing we are trying to do is, which takes interest from all different fields right now, fields with the AI, where we want to embedding haptic experience with the AI. So I will talk about that. So these are the work. Let me see. Oops. So these are the work that I will just talk about today. So first is motion-to-tactile frameworks. We actually did this demo last year and in the WIS, and it actually got a lot of the attention. So what we did is that we have the motion data. Previously, there's no 3D motion to tactile haptic rendering. So there was visual salience-based 2D to haptic, but there's no 3D motion-based. So why do we need the 3D motion is the question. So we need 3D motion to haptic is that actually even in the 2D, even if you move forward and backward, previous algorithm doesn't do anything. So haptic doesn't really work at all if you move forward and backward. Because in the 2D, it's same visual saliency. So also with the audio only, the problem is if the audio is there, but if the character is not moving, the haptic really doesn't trigger. So we want to focus on whether we can actually get the context of the motion of the avatar, or at the time, it was the COVID time. So we were working with those virtual concert projects. So that's why we were trying to convert the virtual concert avatar moving to the the upper body haptics. So we work with the B-haptics. This is one of the company in Korea working on commercial level, the haptic suit, haptic glove, haptic band. They sell all sorts of the haptic devices. And what we have done is we look at the concert and we figure out that there are many of the motions is actually happening there's a choreographic motions involved in the virtual avatar concert, meaning that they are pointing someone or they are waving rather than dancing in the virtual concert. So actually that's where we get started. And main idea here is we get this kind of motion, motion salient MST here is element points for the motion saliency. And we put the base components here, 3 components. So here, red dot is actually the very active joints. And blue one is the center joint. So we actually form a relationship between that. And this yellow one is actually where the haptic rendering is happening. So we had 2 different ones. The one is the tactile localization, where we decide where to put the tactile stuff, the rendering. And second thing is the tactile intensity, how we get change the intensity of the tactile. So here, based on in terms of the localization, we use the 3D warping from this bodily movements. And in terms of use the 3D warping and direct surface mapping. And in the out of range, we have to do the out of range mapping that goes into within the boundary and do the 3D warping again to get the localization done. And so this is how they work after the real-time implementation. So you can see that the large range of motion, it actually moves around with the high intensity. And with the small range, it moves with the small intensity. And we can also get the different pushing motion with the real-time, with the different changing in the intensity here, which doesn't really work with the 2D visual saliency work. So this is how they work in the real time. So this is what we use. So this is actually the real-time working of the system that is providing to the different areas of the upper suit. Yeah.
What are the things on the vest? Are those are sensors to get the to get the data?
No, so in terms of the sensing, we actually used at that time we used I think, let me just go. That one is actually, we don't get the sensing from this suit, it's just the actuation.
Okay.
So the thing is, we get the sensor from, I mean, what we are translating is the motion of the avatar. Mm-hmm. So we get 3D motion from the avatar itself. So translating into the haptic, yeah.
Okay.
And second thing is about the designing haptic experience in situ in VR. So this one is actually, we found that, as I mentioned earlier, they didn't have this kind of rendering the haptic. I mean, then recent one, they have the haptic with this simple UI drawing. We found out that there is a problem here, is that based on the different hand gestures, so this is what we measure with the accelerometer on the hand. So based on the different hand gesture, even you vibrate the same location, you get the different actual acceleration propagation on the hand. So we figured out from our preliminary study, and we picked out 5 main VR pose that is frequently used for the gaming, and we found that whether we can compensate this kind of differentiation with the framework. So meaning that if the user draws something like Z in their hand, whether they can be maintained in different hand pose, whether we can make that happen. So that's what we have started on. So that's why we started with this validation, because I guess the reviewer will ask, have you validated whether it's really different? So that's why we measured the accelerometer, yeah, around the hand. Maybe I think more than 15 accelerometer on the hand, yeah. And this is the current baseline. So this is what happens. So if you actually have a different hand pose, even if you want to draw like this, you design like this, actually it's actually vibrating in this way. So you get the different feeling out of it. So this is how you get really fit with the current design. So with the posture adaptive algorithm, what we want to do is getting the same perception of the vibration on different hand postures. So to do that, we have several stages. So we have the basically user input. They just draw it in VR. And we have this phantom grid and the phantom sensation. So phantom sensation is well-known of effect in Kai. It's actually populated in Kai, where if you vibrate two things together with a different intensity and timing, you get the vibration in the middle. That's how you get perceived. So there's a 1D phantom and 2D phantom is that these gray ones are the actual vibration. These blue ones are the vibration you perceive. So if you have 2 of them, you can get the 1D line. If you have 3 vibrations, then you can actually move in the 2D area within the boundary. So based on this relationship, we actually used to design our haptic feedback. So to do that, we first need to find out how to construct this grid. So we had several areas in the hand, finger to finger, finger to palm, and palm to palm. So all different regions have different construction of the phantom grid. So we constructed phantom grid based on the hand configuration. And after that, we have to know that whether we have had this kind of coordinate positions like this. We want to do this. So we know that the different grasp has a different finger. We have this state, the variables there. So we know that when his finger is open or when his finger is at the palm. So when it's hitting at the palm, we are actually changing this boundary. So this is how the hand is in the thumbs up like this. We have all the hands are collided with each other. So that's how we set the whole boundary of the vibration. So this is a kind of base sketch that we start for our vibration. And based on this, then we actually get this one based on this vibration. Here, one thing we didn't consider was the actual contact from the finger to palm. Here, the only assumption we had was we don't actually touch it with the full contact to contact, because that will actually unify the vibration anyway. We will have the similar effect. So based on that, we run this algorithm, and this is how they do in the in situ VR haptic design procedure. And we actually did it with the users to do this kind of design by themselves compared to the baseline of designing and see whether they can feel the difference. And we found that they really see the difference when they perceive the difference. And here they can just throw the haptic device and play, and that's just right? Everything is happening in the back side, so they don't really care about what's happening on the front side. And this is the real-time working. Yeah, so you can draw it with any hand pose, and you can the play meaning that they play the vibration on the hand. So we actually had a prototype of the glove with 15 to 17 actuators. Yeah. Yeah. So this is all algorithms that I mentioned, and this is a different scenario that they use. So we give the task for the play for the design for the gaming effect. Yeah, something like that. And in terms of the multimodal haptic interface, I'll just go briefly. I think I consulted when Mike was there and Michel was there. I think I acknowledged you guys in the paper because communication was kind of stopped. But we actually got some inspiration about getting the force feedback from the palm. And this one is actually getting the main thing is here is the rendering the different physical properties, inertia, or the fluid viscosity, and those things with the palm, whether they can actually perceive it, and we did it. And second thing we did, I think this was presented in Ubicom 2 weeks ago, is that about getting the force feedback to the different phalanx of the thing. So here the main stuff is we actually made this brake, the electrostatic brake, to make the hand force work. Stop going forward for each phalanx. And we see that the main finding from this one is that we see that there is a difference when you actually stop the finger at the fingertip and the inner fingertip. But middle one, it doesn't really matter. Yeah, we can skip that, or we can actually coordinate differently during the interaction design. And this one is about the thermal one that we are actually presenting in this ISMAR. We actually built this device, the glove, kind of bulky, but I think my student covered everything with the cover glove, so it looks nice, but internally it's not look as nice as this. Yeah, like this. Yeah. So what we hear is that we are the first one to actually see whether we can provide the dynamic thermal sensation over the whole hand. So we use the same phantom grid, but what we actually did is we use this thermal peltier. It's a flexible one. It can be actually used in the glove. So it can be actually bent a little bit in some range of the angle. And we can actually did a user test on the perception level whether they can actually discriminate it. So we actually did this one. And we found that they can actually discriminate different dynamic thermal sensation on the palm and the finger, up to the finger. And we don't really need to equip the whole hand with the whole peltier. We have only these red ones are only the peltier areas. So we only had 4 peltier. And this vibration, it can be also reduced because we did it for the whole testing on the whole area of the hand, but it can be skipped. So it can give enough. And we actually did the test on this hardware. So it can be turned on for more than 90 seconds. So intermittently, previous works only used for the 10 to 15 seconds, and they don't mention about anything after that. But this one can actually, with the PID control, we can maintain up to 90 seconds. So I don't think people will do the warm sensation more than 90 seconds. So that's one thing. Yeah. And this last one is the work that ongoing is that we do the generative text-to vibration. So we figure out in the haptics area field is that there's not a single work that do the generative, the text to vibration. It's about just the text mapping to vibration. So that's how it works. So this is the concept here. We get the prompt like this. This is like the prompt from the haptic designer from the industry. We actually get the expert level design. We did the interview with the 5 designers, and that's actually working in the haptic company. And they are actually doing this kind of stuff. They want to give this kind of prompt and get something out of it, because they don't want to start with the very blank stuff to make the vibration. So we use that prompt to go to the text-to-vibration model. And here, the training and alignment data set. So here, we put the expert-voted haptic data set where we collect the data from the users and the experts. And these ones is actually aligned with the converted audio to haptics signal data set for the fine-tuning, and we get the biotactile signal output. So this is just the video out of it. So previous limitation is like this, is that you need to, I think this is one there. So limitation of the current Gen AI models for haptic generation, you don't really have anything. And second thing is you have to everything is really on the focusing on audio to haptic parameter tuning, just about that. And that doesn't really give anything other than intensity change. So in terms of the pattern shape, everything you have to make your own. And building and overcoming the obstacles in the design framework, you have to building a user interface without the HMD. So that's one of them. And here is what we have done. We have the initial data development. We have the haptic database training this model, building a user interface. And in our user interface, it's just the GUI with the prompt and getting the actual output. And in the optimization process, we did this fine-tuning haptic check with the improving user interface. We did the final evaluation. So in the final evaluation, we compare with the baseline audio to haptic. So here, we use the based on the audio gen encodec. And actually, here, I think the main part here is that I think not these ones, but it's more about getting the user data out of it. So we use this. We made this interface here. And these are the prompt, and these are the candidates of the different models. So we use this for the comparison. So model A, B, so they don't know which one is which one. So we compare with ours with the previous audio to haptic to see whether they see the difference. Yeah. And currently we have some, these are currently the output of the model based on the prompt. So there's a different prompt. There's an emotion theme or game theme. And based on they had this evaluation. Usually they don't get the perfect score in our model. So it's maybe 4:1 ratio of the preference from the designer and the general users as well. So that's the one. And I think this is the last one is work in progress. We see that there's a lot of work going on to embed the understanding the scene visually. But we see that even after the understanding visually, we want to see whether how haptic can be involved, why it's not really popularized, is that we found that if you want to put only thing in the virtual scene, how haptic is used is they use it for the collider-based tactile vibration. That's the really only thing that is used. So we want to see whether we can embed the haptic with the different, maybe we can embed, if we know the context, we can embed tactile or we can even force, or if the thermal one is coming in the future, then we can also put the thermal contact sensation as well, right? So in that case, we want to see whether we can embed the haptic design with a physical proxy or virtual object. And that's what we are actually trying to do with the design prompt and see whether we can get the physical object proxy and the haptic feedback all together with those. For these ones, I believe we are, I think we are in the early stage, but we need to make our own data set as well. Because this typical, this specific area application always require this kind of fine-tuned data. And this is what we are envisioning here, is using the physical scene to getting the virtual scene candidates. And after that, we want to use it for the scene designer or virtual scene designer, where they can design the scene with the feedback in it, because they don't want to design the scene and doing the feedback design again. So that's what we want to do with this one. So for the quick recap, so I think I just want to focus on the leveraging the human body and the object and the surrounding space. That's how we should go for even in the glasses or even after the glasses or even without the glasses. And I think we need a better understanding of the context and the deeper intention of the user, which I think is still missing because we are still mainly relying on the touching the body surface. Yeah. And second thing is missing physicality in the XR scene. We need to bring the essential multimodal physical feedback. So I think maybe in the very near future, maybe force feedback like squeezing could be one of them. And I think maybe thermal is getting there because thermal used to be not used at all because of those heat issue, but nowadays with the better material set, I think it's really getting stable. And entire haptic feedback with the design framework. So this is what I have worked on, and yeah, that's all I have today. And yeah, thanks for your time. Yeah, thank you.
Thank you so much. Thank you so much, Sang-ho. Yeah, I might stay sitting when I talk, if that's okay. But so I think it's actually super interesting, and also I can see if that's more a comment than or a note than a question. Is I could see like some of the sensing techniques that you have, and also the haptic feedback could be used also beyond XR, like maybe for other type of tasks that are. So I think it can be generalized actually, which is interesting. And I don't know if people have questions, whether it's online or in the room.
I have a couple questions.
Yeah.
Especially on the first half, like in the sensing techniques. First of all, with the gaze one, which is very interesting. I know this is like in progress, but so you're using the gaze signal to try to distinguish grasps or grasp intentions, and you're trying to distinguish grasp to move versus grasp to use, right? And so it sounds like you feel like you've seen different patterns of the gaze behavior, but do you have like have you done any descriptive statistics of just showing like how different is the gaze in one versus the other, and like how much signal is there to work with?
Yeah, I think this is still ongoing, and I think one thing we are actually critically looking at is the affordance of each object. So in each object, they have the affordance, and based on those affordance, we found that there's a data set that people, when they have this object and they want to use it, then there's an area that they are touching or they're trying to hold on to it. So that's I think the main differentiator when you want to move it or actually use it. Because when you want to use the pot, for the gaze movement or the gaze tracking data is about more related to the area where they are going to actually hold on. On the other hand, in terms of the manipulation, it's pretty random. There's not really the pattern that we saw. So I think that's the main differentiator we saw at this point. Yeah.
And is there personalization too, like the way my patterns might be different than Sean's?
Yeah, that's the good question. I think that's why I feel a bit lucky that I'm in academia, because they always have per user accuracy in the paper. And when we look at it for now, I think it really depends on the person by person at this point. Because I think it might be different in the near future, but we are currently using the Barrio. It has a very high performance, the eye tracker. It's a 200 hertz frame. I think it's better than any other headset maker, but still we get that data pattern, where behavior, where it's really more better for the person. And even for the session-wise, session-wise it's actually much better because they have a fixed setup, the fixed calibration. Yeah, so in terms of the multi-session is better, robust, but in terms of the multi-person, across the person is a little bit less, yeah.
I think Andy has a question.
Andy?
Yeah, welcome back to Building 99.
Yeah.
And thanks for showing us all this amazing work. I'm just thinking a little bit on the lines. You've studied a lot of different grasping techniques and how people actually grasp real objects, and to some extent, grasping haptic proxies and that sort of thing. What do people do when they're faced with the challenge of grasping just pure virtual objects? Do they change their behavior depending upon what the object is when maybe they don't need to? How does this sort of transfer to, how does all this sort of relate to the problem of grasping an object that's not really there?
Yeah, I think that one, we actually I think that one is related to our work on the multi-phalanx force feedback glove. So we actually did a test with the baseline where they had this nothing there, no force feedback at all. And if there's a force feedback with the different phalanx for the triangle, cone, or sphere, we actually see that if it's there, of course they feel more better or more immersive. But even if it's not there, I found that they don't really go full grasp. If it's virtual, they really corresponding with the visual wise. So that's why even for the haptic, haptics and those people are actually advertising we need a very high resolution of everything. But in my opinion, if visual proxy is there, we just need the key points to provide the haptics. Yeah, dominant area will be the fingertip, but I think the other area can be the very inner side of the finger. Those can be we have to find those dominant key points to provide the appropriate feedback. Yeah.
It strikes me that you were talking a little bit about the self-touching behavior, and I was kind of wondering, do you observe people adopting kind of a pinching gesture that would sort of be analogous to, like, if I were to pick up a coffee cup. In real life, the coffee cup would sort of oppose my grasp, right? And so I would never actually be, my fingertips wouldn't be touching. But without an actual coffee cup there, my fingertips might eventually start touching each other. And I might even sort of like grasp or sort of squeeze, those fingertips together at a kind of a force that's appropriate for a coffee cup, right? So I'm just kind of wondering if maybe people sort of like, kind of play along or go with, forces in that sort of grasping maneuver, that sort of self-touching thing, in a way that's kind of consistent with what they know in the real world. I don't know. It's I think it's a little early to be asking some of these questions, but it's like good research stuff.
Yeah, but I feel like more like if I have because I also experienced this works with my own hand, is that I think people usually adapt to the visual proxy quite fast. So, and in terms of the force feedback, I mean, it's like TV. So, I mean, you have a high performance TV and you don't know it's really good or not if you see right beside the old TV, right? I think that force feedback is similar. If they feel it and they feel it that they never felt it, then they know it's much better and it's good. But if they start with not providing those feedback at first, they think it's kind of okay based on the visual proxy. And visual proxy, what I mean is that we still need to keep the line that where it doesn't really work against the ground truth rule, meaning that as you mentioned, when you're trying to grasp a cup, the finger shouldn't touch, right? So at least we can do some control to display trick to actually, our hand is actually touching the cup even before it's actually getting into it, right? So at least I think those are why I think mixed reality researchers are heavily working on those control to display ratio, I think. But I think after everyone gets into maybe if there's a good feedback interface, they feel it once, then they might not want to, go back. Maybe, that's my assumption, maybe in the future, but yeah, that's my take on,
Thank you.
Just following up on Andy's there, do you distinguish between the communication, like the feedback of the fact that an object has a surface versus the fact that it has weight? And are both of those important, or is just having a surface is enough? Because I can imagine, if I think about the different ways I might grasp a virtual box, right? If there's no haptic feedback, I might just kind of grab, my fingers might go through the edges of it, but it's fine. If it has if I'm getting feedback that there's a surface, but it's still kind of weightless, I might kind of still grab on the surface, but I might still just do it like this, because it's big, but it just has no weight. But if it actually has some weight behind it, then I might do it like a real box with both hands. And so do you see those kinds of differences, and do you distinguish between those different kinds of, I guess, haptic feedback?
It's very hard to answer, but I think currently people are working on the surface quite a bit, is that it's actually, we can implement now. In terms of weight, it's very hard to make the weight out of it. Sure. So I think that's why they are heavily onto the control to display for those weight issue. Okay. So I think that's why, I think the bank already made the publication in 2017 or so, I think, about those, and I think people keep tracking those. I think those kind of research, that line of research is keep going, because I recently also read it, and that research is keep publishing. And right now, I saw a very recent one from our department. There's another professor who's actually working on how to make it this control to display ratio better, even with the haptic proxy together. Yeah. Because there's a boundary of the threshold, and they want to increase the threshold with the haptic proxy. So I think that's what they are trying to do. But in terms of weight, there will be a big difference in my opinion. But the thing is, physically, it's very hard to implement. Yeah.
Great. Any other questions?
I have another meeting. I have to jump. Thank you very much.
Yeah, thank you. Thank you for here.
Hopefully we'll see some of your students in the future.
Yeah.
Okay, we are talking about that.
Yes.
Great.
Bye.
Yeah.
Yeah, so if there's no other question, thank you so much again.
Yeah, thank you.
And great.